So the second major criteria that affects spontaneity of a reaction, so aside from the enthalpy, the bond energy change that occurs, is this thing called the entropy change. And entropy is a capital S for our calculations. It's a measure of the relative disorder of a system. So the more disordered the system is, the more entropy that exists. Increasing entropy is spontaneous. Always. So there's always a natural process for, a desire for all disorder to increase during a reaction. So delta S for a reaction be the final entropy minus the initial entropy, which is also products minus reactants, just like our delta H calculations. So eventually we see delta S, usually at standard conditions for a reaction, would be delta S for the products minus delta S of the reactants. Those calculations are going to work just like delta H, but with different numbers, because now we're dealing with entropy instead of enthalpy. Okay? So for a natural process, a natural spontaneous process, the final entropy is typically larger than the initial. So there's an increase overall in entropy for spontaneous entropy-driven processes. So if we think about the things I mentioned in the last video that were spontaneous, that were endothermic, something like melting ice, something that requires heat. We have to put heat in to melt the ice, the enthalpy of fusion. But it's spontaneous because entropy balances out that difference in enthalpy, the energy that we're putting in. Melting ice is spontaneous because of entropy. So the H2O molecules is a liquid. Have more freedom, we call it freedom, than solid. Or the H2O molecules that are in ice. There's more random movement in liquid water than there is in solid water. That's a measure of disorder. So H2O is a liquid. Is more disordered than water as a solid, because the liquid molecules can move all throughout their container. The solid water molecules in ice are locked in a crystal lattice, and they don't have the ability to move around. So the solid water is more ordered than the liquid water, which means they have less entropy because they're more ordered than the ones that are more disordered. So there are a few factors that influence the value of entropy. Things that will affect the delta S that we calculate when we calculate delta S. Number one, the volume that things are operated at. This is especially true for gases, because the gases are compressible. Solids and liquids aren't very compressible, so we can't really change their volume very appreciably. But we can compress a gas very easily. So for gases, as the volume of a gas sample goes up, not changing how many molecules, not adding more, But as we take a sealed container and expand its volume, the entropy goes up. And the way to think about that is that when we increase the volume of a gas sample, we give each molecule of the gas more freedom to move around, more elbow room in the container. That's more disorder. The more tightly they're packed, the more ordered they have to be in order to be in that container. But as we decrease the number of molecules per unit volume in the container, we increase the entropy. So each molecule has more space to move around in. And that's also why gases mix freely, even if they're not the same gas. We dump some O2 gas in with N2 and they're immediately mixed together because they have a lot of entropy, high entropy. Number 2, temperature. As temperature goes up, all molecules move more quickly. We've talked about that some back in the gas chapter. As we increase the temperature of the gas, all the gas molecules have more energy. Their mass didn't change, but they have more kinetic energy, which means they have to move faster. They start moving faster and faster. The faster something's moving, the more entropy it has. If we cool a gas down to 0 Kelvin, cool a material down to 0 Kelvin, that's the only time when entropy equals 0. So absolute 0 Kelvin is a theoretical temperature. We can't get to 0 Kelvin. We get awfully close. We spend a lot of money, but we can't get quite to 0 Kelvin. But at 0 Kelvin, all molecular motion ceases. So no molecules are vibrating around or spinning like a top or moving from one place to another. They're totally frozen. Everything absolutely freezes at absolute 0. But at any rate, as the temperature goes up, there's more randomness, more chaos in the system. That's an increase in entropy. So S goes up as motion goes up or temperature goes up. They're all related to each other. Number 3. Physical states. Each state has a characteristic range of entropies. So the gases have greater entropy than the liquids, which have greater entropy than solids. Because of the ability for the molecules to move around. Item number 4 is number of particles. The concentration, as we change concentrations. Low concentration solutions have more entropy than high concentration solutions because the more molecules or ions that you pack into the same volume, the more ordered it is, the less elbow room each one has. So as concentrations decrease, entropy goes up. All of the individual solute molecules or gas molecules, this number 4 is really the same thing as number 1. Because if we take a gas and expand it, we dilute the gas molecules. So it's the same concept here. So as you dilute something, you increase the entropy, you increase the randomness, because each molecule has more room. There's less interaction. So if we tie this into what we're all doing right now, which should be social distancing because of the coronavirus, we're social distancing, we're giving ourselves more elbow room. All of us have increased our entropy because no longer for 3 hours a week are we all gathered in one room. That's a high order situation, even if you're not sitting in the same spots. That's a high order situation. Right now we have all gone through a significant change in entropy. We're all in different spots than we used to be, and there's a lot more space between all of us. Along with concentrations, it's about size of particles. As we take big molecules and break them into smaller ones, we increase the entropy. Because big molecules, it's harder for big molecules to move around. A bunch of tiny molecules have much more randomness than one big molecule. So think about a Lego set that you bought. All the pieces are separated. That's a lot of entropy. When you put them all together to make one big thing, that's very ordered. Okay? Take that thing and bust it back apart. Now you increase the entropy compared to where you had it when it was all put together. Okay? Same kind of idea. So a big organic molecule that we burn comes in a little small CO2s and H2Os. That's an increase in entropy because all the little molecules have more freedom to move around than that one big one did. All right, we come back, I'm going to show some examples of some equations, and we're going to guess what the value, either positive or negative, is for each entropy situation. Okay?